Good afternoon, Year 12. In today's lesson, we're going to revise the work that we covered before the holidays. So as you know, before the holidays, we started Unit 4 with our first topic, which was compound interest loans and investments. And we started looking at recurrence relations and how we could model compound interest loans and investments using a recurrence relation. So you'll remember from our work in the sequences topic that we did in Unit 3 that recurrence relations have two parts to them. They have a starting part, the initial value, and then they have a rule that can be used to generate the successive terms in that sequence. Before we look at the recurrence relation for compound interest, I'd just like to look at an example with you. If we consider an example where $5,000 is invested at 8% per annum, compounding annually. We're starting there with a balance of $5,000. If we wanted to work out how much that investment would be worth after 1 year, we would want to increase that $5,000 by 8%. In order to increase $5,000 by 8%, we know that we'd need to multiply it by 1.08. And when we do that, we get $5,400. That would be the balance of the investment after 1 year. If we then wanted to work out the value of the investment after 2 years, once again we would need to increase this amount here by 8%. In order to do that, we would need to multiply it by 1.08. giving us an answer of $5,832. That would be the balance of the investment after 2 years. If we wanted to figure out the balance of the investment after 3 years, once again, we would need to increase it by 8% by multiplying by 1.08. Let's have a look now at how that translates to the recurrence relation for compound interest. So for compound interest, the recurrence relation that is defined on your formula sheet is here in this red box. So an plus 1 is equal to r times an, and a0 is our initial value. The r value that is here is defined as 1 plus the interest rate as a decimal per compounding period. What that means is to get the next term in the sequence, you need to multiply the previous term by 1 plus the interest rate per compounding period, and that interest rate has to be as a decimal. We can see then that this rule is following exactly the same process that we just followed in the example that we did together. So we had an initial value of $5,000 and we were wanting to increase that by 8% per year. So our interest rate per compounding period was 8%. We know that to work out the balance of that investment after 1 year, we multiplied the initial value by 1.08 in order to increase that $5,000 by 8%. So this recurrence relation that we use here for compound interest is doing exactly what we did using our common sense approach in the example that we looked at earlier. So this example here says that $5,000 is invested at 3.4% per annum compounding quarterly, and we're asked to use a recurrence relation to model this situation and use it to determine the value of the investment for the first 4 quarters. So I've written the formula here straight from the formula sheet. You'll notice that the formula sheet doesn't include the A0 part. We need to remember to include that bit ourselves. Over to the side here, I'm going to work out the R value. So I have recognized that in this situation, interest is compounding quarterly, and so the R value becomes 1 plus the 0.034, which is our yearly interest rate, divided by 4 to work out our interest rate per quarter. That gives us a value of 1.0085. In our recurrence relation then, that becomes an plus 1 is equal to 1.0085 times an, where a0, or our starting point, is 5,000. So down here, in order to generate the first 4 terms of that sequence, or determine the value of the investment for the first 4 quarters, as the question asks, I'm starting here with the initial value of 5,000, and in brackets here I've followed this recurrence relation, which says to multiply your term by 1.0085 in order to get your next term. So I've just put that bit in brackets. When I carry out that calculation, I'm working out the value of my investment after 1 quarter. To get the next term, I follow my recurrence relation again, which says to multiply by 1.0085 to get the balance after 2 quarters. Follow that same process again to get the balance after 3 quarters, and once again to get the balance after 4 quarters. Now we have looked at this before, but I just want to briefly go over how we can do this very easily on our green calculators, because you may be required to generate the first 12 terms in one of these sequences, and we don't want to be wasting time typing these numbers into our calculator repeatedly. So on our green calculator here, in order to generate these sequences very quickly, we start with the initial value. In my case, that was 5,000. And after I put that initial value in, I just press enter. I'm then going to put the times by 1.0085, and you'll notice the calculator has picked up that answer before the previous answer of 5,000 and is going to multiply that by 1.0085. When I press enter, I'm now getting this answer over here of 5,042.50. Rather than having to multiply by 1.0085 again, I can just now simply press enter. And you'll see that the calculator has picked up that previous answer and is now multiplying it by that same number again. And that's giving my answer over here of 2 quarters. Press answer again, and I'm going to get my 3/4 balance, and press enter one last time to get the final balance that's there. So I'll remind you of that again in the lessons that are coming up, but that's a really important skill to be able to generate those terms very quickly on your calculator. The other thing that we looked at before the holidays was we revised compound interest briefly, and in particular we focused on looking at the effect of the interest rate and the number of compounding periods on the future value of our loan or investment. In order to look at that, we first of all needed to remind ourselves of the compound interest rule that we have learnt previously, and there it is there. So we know that A is the future value or the future amount of our investment or loan, P is the initial value or the principal, I is the interest rate as a decimal per compounding period, and N up here is the number of compounding periods. So how then does the interest rate affect the future value of the loan or the investment? In order to investigate that, we've got a brief example here where $5,000 is invested for 5 years with interest compounding annually, and we're asked to calculate the future value of the investment if the interest rate is 7% per annum, and then again if the interest rate is 9%. So if the interest rate is 7%, we've got it compounding annually, therefore the interest rate per compounding period as a decimal becomes 0.07. And to get from that 7% to 0.07, all we've done is divided by 100. And N, the number of compounding periods, this is happening for 5 years, once a year because it's compounding annually, so our N value is going to be 5. We've put our initial value or principal of 5,000 plus our I and N values in here to get a future value of $7,012.76. In the second one, if we look at the same situation, the only difference being our interest rate now has changed to 9%. So you'll see that change that's happened over here. When we put all of those numbers in, we get $7,693.12 as our future value for our investment. I think most of us would have known before we started this that the higher interest rate is going to cause the investment or loan to grow more quickly. And if we had a choice between these two interest rates and we had an investment situation, we of course would want to go with this highest interest rate. If we had a loan situation, we'd want to go with the lower interest rate because obviously we want to pay less interest in a loan situation. How then does the compounding frequency or the number of compounding periods affect the future value of the loan or investment? So we've got a situation where we have a loan of $7,000 being repaid after 5 years. We're going to calculate the future value of that loan if the interest rate is 8.4% per annum, compounding monthly or compounding daily. So the first one here, when we have it compounding monthly, the I value becomes 0.084 divided by 12 times in a year. So the interest rate per compounding period becomes 0.007, and the number of compounding periods, this loan is for 5 years and it's compounding every month, so 12 times in 1 year. So 5 times 12 gives us our 60. Put all of those numbers in and we get a future value of $10,638.15. If that investment is now compounding daily, when I work out my new interest rate here, when I do that value on the calculator, I get a really long decimal. I don't want to have to write down all of the decimal places for that number, and I also do not want to round that value because otherwise my final answer won't be accurate. So you'll see here I've chosen to take that over as a fraction so that I retain its exact value without having to write down all the decimal places. Down here we have 5 years once again, but this time 365 times in a year it's compounding because it's compounding every single day. That gives us an end value of 1,825, and when we put those values in, we get $10,653.22. And we can see there that the future value here is higher than the future value was in Part A. So therefore we can conclude that the more frequently you compound, the quicker that investment or loan is going to grow. So we've got that down here that the interest earned or paid is greater when the investment or loan compounds more frequently. For example, if you're compounding monthly, your investment or loan is going to grow much quicker than if you're compounding yearly. That's the end of the work for the first lesson, which is our review lesson. In your OneNote, you will find that there is a very brief worksheet. It only has 5 questions in it, which goes through the concepts that we've covered here. The reason that there are only 5 questions is because we've covered these exercises before the holidays. So there's a note there for you that if after doing those 5 questions you feel that you'd like a little bit more practice on this work, we have referred you to the exercises in the textbook that can help you with that.